Hey guys, I just thought I'd do a video so we can go through this final lesson on the topic. So we're looking at flow problems. So a good way to think about these lessons, also apologizing for my voice, dealing with some COVID at the moment, so I'll be doing my best. All right. So with these flow problems, think of it as, water going through pipes or traffic on roads, and so the sentence here is talking about mail deliveries possibly as well. And remember we spoke about in class the source and the sink is another way of having a start and end point. So I thought I'd actually start with the example on the second page. I think it's a nicer example just to show you this overview. Let's just read through what this question's asking and I'll talk through it with you. Find the maximum flow with the network from S to T. So the maximum flow. So let's think, my brain always likes to think of them as water flowing through a pipe. So from the source to the sink, S to T, there's 3 routes the water could take. Along that route that I've just done in yellow there, we're looking at the smallest number. 5, I'm going to circle it. 5 is my smallest number, which means that the most water that can flow through that entire path from S to T along that yellow route is 5. So it's always going to be that smallest value because you can't have any more than that fitting through. So I turn all of them to 5. Now I'm looking at my second route, my green route here, 11 and 14. Take the smallest number is 11. So the most it's going to be able to carry through there is 11. And my final route in red here would be 4. So now when I'm going to answer the question, what I'm always going to do is I'm looking at the flow coming from the 3, in this case, 3 edges coming into my final part, which in this case is T. And when I add those 3 answers together, I get my maximum flow. So the maximum flow of this whole network from the source to the sink or from S to T is 20. I don't know any context. It could be cars, could be liters, who knows. But that's essentially the method we're going to start by using. There is another method we're going to look at in a moment, but now let's come back up here. Now this diagram here is just showing how we talk about the flow and how no matter what you have, these larger values coming into it, you can always only take the smaller number. So let's look at this second example here now. Well, example 1 it is. This time we've got a few more routes. So when it's something like this, especially with the vertices labelled, I like to write out my different options or ways you could get around from the start to the finish. Whereas this first one we did was pretty basic, 3 different options, so I didn't worry too much. But looking at this one, if I start with my first option, SACT, straight across there. Again, let's employ that same tactic, 200. So I've got my first route done, 200. Notice on the line from S to A, I could fit, say, 500, let's say, litres of water, but I'm only using 200 in that particular pipe. Keep that in mind. If we go now to SADT, S-A-D, then T. So going along this route, again, I'm going to take my smallest number, which would be the 100. So I'm going to use 100 here, and I'm going to use 100. What I need to be careful of is this part here, where I'm using more than one amount, you could say. I can't go over 500, because that particular pipe from S to A can only hold 500 litres. So far, the yellow path has used 200, and the green path has used 100. So I've only used 300, so I'm still fine. So keep that in mind. So I'll fill in over here that it's 100. Now I've got my blue path. Should be an S there. SA, change my pen type. SACDT, SACDT. So that's now coming down. I'd look along this and I go, oh, okay, I could use the 50. But hang on. Going from, I knew that was going to happen. Going from A to C, when I was using 200, I used all 200 litres. So I can't now go, oh, I'm also going to use another 50 there. I've used all my amount there in that pipe. So no more could hold in that pipe. My yellow path used up the full 200 litres. So what that means is the path SACDT, this blue path, nothing's going to flow through it. And my final path I'll do here in, let's go purple, SABT. Smallest number is 150. Making sure I'm not going over that 500 on that first one where I'm overlapping, and I'm not. Okay, so I'm using a total of 450 and that first pipe, which is under 500, so I'm fine. Now I know this, I do the same thing I did in the last question. I'm looking at the values of the pipes that lead directly into the sink, that final vertex. I did them before in black, so I'll do them in black again. I only want the value of these 3 pipes, which tells me I'm going to add those 3 values together, and I'll get my answer of 450. And that there is my maximum flow of, and this one is traffic. Okay, so can you pause the video and have a read through this and see how you go with the question yourself now? So press pause. All right, I'll assume that you've given it a go. You've now had your answer written in your book, and let's check it. What is the maximum traffic flow from towns A to G, passing through B, C, and D? So we are going this way, and hopefully you got the maximum flow is going to be 200. All right, what is the overall maximum flow? So now I'm just going to check the other route, checking the blue route. And the smallest number is 250. So I'll make that 250 and that 250. And what do I do for my maximum flow? I'm looking at just the 2 edges coming into the sink and what the maximum flow is. So it's 200 plus 250 gives me 450. Okay, now this is where they sort of add in usually pretty common a problem solving question. If we build a new road from E to D, carrying 400 cars per hour, how much would the maximum traffic flow increase? Okay, well, let's add it in. From E to D. That means I'm going this way and I'm adding in 400. All that does now is it adds in a third possible path. So if I get a bit tricky now, I write out, okay, so A, B, C, D, G, remember that was 200. Then I had A, E, F, G, that was 250. So now if I add in my green route, let's go A, E, D, G. Let's work it out. Well, smallest number would be 400. My only problem is though, step back and look at the whole thing here. My only problem is I can't use 400 out of the pipe A to E because I've already used 250 out of what it could hold 400. And the pipe, or I should call these roads now, shouldn't I? Because they're towns. The road DG, it could hold 500, but I've already used 200 from another route I've used. So I could use 300 out of the road left over from D to G, but I could only use 150 to make up, remember that road A to E could only hold 400 cars. And my blue route is using 250, which means the most my green route can use is 150 cars. So that means that is my maximum flow along that route. Now, the question is asking in here, by how much will the maximum traffic flow increase from A to E? So overall, how much will that increase? So all it's saying is, well, remember, your maximum flow, you're only ever adding together the two edges that are coming into the endpoint. So I'd be adding the blue 250, but I wouldn't be adding that with the original 200. The road DG can now hold 150 plus 200, so 350. So now my maximum flow becomes 600 cars. It does get a bit tricky, but you just have to be careful not to overflow the roads. Those original numbers are the maximum cars it can hold on that road. All right, now that's just talking about remembering the source and sink. You might be thinking, oh gosh, miss, that's a lot to take in and I'm getting confused. Or you might be thinking, yep, I can see that. Good news for the people who are not liking any of that method so far. There is another method. It's called minimum cut. So I like this method, and this method, it'll always work no matter how complicated. Some people don't like this method though, because it is a bit of a guess and check method. So let me explain it. And you'll read through here, I've said it is difficult to do this other method at times, and you can see how it does get a bit hairy in some contexts. So before I introduce the second method, the first thing you need to know is what a cut is. A cut is a line that we can draw through this network. We represent it with the dotted line, as you can see in these examples. And it has to completely cut off the flow from the source to the sink. If this cut does not stop the flow from source to sink, then we are not calling it a cut. It's not a cut. So what do I mean? Let's look at these two examples here. Back to water in pipes. You want to stop the water getting from the source to the sink. There's something going wrong with the plumbing and you need to cut off all water. So this dotted line here, passing through, it's going to stop the water coming through that point there. It's going to stop the water coming through that point there, and that point there. There's a reason I didn't do this point. That point there is in fact irrelevant. It doesn't have to cut through that point because look, the water's not going to be able to get through anywhere to be able to come around and go in this direction. So there's no need for that cut to be there. So this example on the left here is a cut because there is no way the water can get from the source to the sink. However, looking at this second example here, you can see my highlighted path shows, well, even though they've drawn this so-called cut, it hasn't stopped the flow. Water could definitely travel along that highlighted part and get from the source to the sink. So we would call this not a cut. All right, so first thing, you know now what a cut is. One thing we need to learn how to do is work out the capacity of a cut. The capacity of the cut is just where you add up the weight of every edge the cut restricts. So for instance, looking at this example, it says calculate the capacity of the 4 cuts shown in the network. Ignore my car diagram on the right here for now. Let's just look at cut 1, C1. That's this cut here. The capacity of this cut, well, it passes through the 2 edges here with a weight of 20 and a weight of 15. So we'd say cut 1 has a capacity of 35. Okay, now think back to this example up the top here, where I pointed out how it was unnecessary for me to show that the cut stopped the water flowing through that point, because there was no way the water was going to, there's no point in the plumber getting glue and gluing up this pipe here at that point. It's a waste of glue, because it's not possible for the water, if he glues up all the other points, it's not possible for the water to ever be able to travel through that pipe anyway. So the way I like to help you remember that, it's all about the direction of the arrow. If the arrow is facing in that certain direction, it's a pointless cut, and we don't count that as a capacity. So the way I remember it is when the arrows are pointing into the cut towards the right, we do count it. But if the arrow was pointing to the left, we would not count it. And that's going, think about it as a driving in a car. And you might think this is the weirdest analogy. Imagine putting a little car on the bottom of each of these cuts. And these cars are traveling. These are not very good cars. These cars are traveling along those dotted lines. If the arrow is passing through the passenger and out the driver door, we count the capacity. If the arrow is going back the other way, we do not count it. I hope that makes sense. So let me show you now an example in cut 2. Let's look at cut 2. All right, cut 2. I've got my car. Let's imagine this car is driving all the way up this cut. It passes through the line here, and that arrow on that line would be passing through, yep, the right way. It's passing through the passenger door, isn't it? So I would count it. So cut 2, I'm going to count the 20. The next line it passes through, my car traveling up here, it would be passing through this line here. But this time, my car is here. That line would be passing through my driver door. So I'm not going to count the 6, because the arrow is pointing through the wrong door. However, finally, when the car keeps on coming up along here, the last line it passes through, or the last edge of my network, is the edge B to C. And what do you know? The arrow is pointing the correct way, so it would be passing through the passenger door, out the driver's door, and it has a weight of 14. So the capacity of that cut is 34. Okay, let's keep moving, keep practicing. Let's go to cut 3. Cut 3, same thing. If you want to pause the video, see how you go on your own. Cut 3, first thing I'm looking at, okay, it's passing through 3 edges. let's look at the direction of the arrows. Nice. This car is going to keep going forward, and every arrow is going to be pushing into the passenger door, which means cut 3, I'm going to be adding 20 plus 15 plus 14. So my cut 3 will be 49. And cut 4, last one, cut 4, orange cut, same thing. Let's look now. Okay, cut 4, 20, the first edge is fine. The 20 is passing through the passenger. When the car's coming along the edge D to C, it would be coming through the driver door, so don't count the 12. But the last edge it travels through, when the car's up here from C to T, 10, we got to count that, passing through the passenger. So the capacity of that cut is 30. Now, what you're thinking probably is, why are we doing this? Well, we can work out the answer to all of these previous questions, what the maximum flow is, by using the formula I've written on the next page. We can find the maximum flow if we can find the minimum cut. So let's look at these 4 different cuts we've drawn here. Out of these 4 cuts, the minimum cut, the smallest cut I got was the 4th cut, which was 30. So if this question asked me for my maximum flow, and they were all the possible cuts I could do, my maximum flow would be 30 because it was the smallest cut possible. So let's look at a question now together, putting all of that together. All right. We're talking about traffic again. And this is actually just looking at that previous example. And they've put the 400 already on it, as they did in the end. It says, draw 2 cuts, one with a cut capacity of 700 and the other with 1300. Okay. Having a look there, I can see one straight away. I'm going to do this dotted line. I'll do it thicker so it's obvious. There's cut 1. I'll call it C1. It has a capacity of 700 because it's 400 and 300. Now, don't forget, both of those arrows needed to be passing through the car's passenger door in order for me to count the 400 and 300, which they do. So that cut has a capacity of 700. Okay, cut 2, 1300. All right, what about if I went like this? Okay, let's check. This one's 300. It would be passing through, the arrow's going the right way. This one's 400, that makes 700. It's passing through the car, going the right way. And the last one's 600, that would make 1300. And yes, the arrow's passing through, so I would call that cut 2. All right, B, draw a cut that gives the smallest cut capacity possible. Okay, the thing with this second method is, it is a guess and check at times. So now I'm just going to be adding some more cuts. So I know this one was 1300. I know this one was 700. Let me try some others. What if I just try one at the end? This one would be 800. So far my smallest is 700. Okay, what about here? If I went through there, yep, arrows are going the right way. The capacity of this cut would be 600. That's smaller. That's good. Is there anything else? I don't believe so. So I'm going to say my cut capacity was 600. And, this is interesting. What did I get for my answer earlier on for my maximum flow? 600. So what relationship do you notice between the maximum flow and the minimum and the smallest cut? Well, this is the relationship we notice. The maximum flow is the minimum cut. Now, this is your choice from here on in. If you liked our first method, that's fine. Do it. If you didn't, the cut will always work. I prefer the cut method because sometimes I find it quicker, and when networks do get more complicated, that first method can get tough, as you saw. The only problem with cuts, it can be guess and check. And as a mathematician, that's not something we love. But let's see how we go. What is the maximum flow? So let's see. Pause the video. Let's do your cuts. See what you get. I always go for the obvious ones. Start and end. They're nice obvious ones. I'm just going to point out here, this last cut I did. Just something to be mindful of. Again, what way are the arrows going is when you do count that cut or when you don't. So I'm going to highlight the 20, I would count it. The 5, I would count it. The 4, yep, I would count it. But that 30, I wouldn't be counting. And finally, the 15, I would count it. I just want to reiterate that because it is important. And what would I get for that one? I would get 24, 44. I can't see any other way around this. Oh, oh no, that wouldn't work either. All right, this is my only downfall for it. Guess and check. So maximum flow, minimum cut is, by the looks of things, 40. I should have just taken this cut here and out there, of course. There we go, 39. Well done if you got that. All right, maximum flow for this one hopefully was 18. You can see where I did it there. Had a few other options, 22, 23, but yes, it was 18. And there's my answers to those last two as well. All right, guys. Now you can go on with the exercise. And that does conclude our topic now. I will be doing a formative on this topic. So once you finish this exercise, prepare for a formative, and it's going to be summary only. Okay. Otherwise, I hope to see you all back soon